I'm grateful for this opportunity to remind you all about how to design whole systems for radical energy efficiency or for water or materials efficiency. And the practice, I'll summarize, applies orthodox engineering principles, but it asks different design questions in a different sequence, so it gets very different answers. By the way, I recently presented a much larger version of this material as a 6-day intensive course that was filmed, and my team is developing various other tools to help turn integrated design from a rare to a common practice. I will not be talking today about energy supply. Modern renewables now provide 2/3 of the world's net additions of generating capacity thanks to their excellent business case. Our bigger challenge is capturing modern negawatts. And few people realize that the world's biggest energy source, bigger than oil, is the energy saved, say just since 1990, 2/3 of it by more efficient end-use technologies. If the United States total primary energy demand had kept growing in lockstep with GDP since '75, we would have used this much energy. Instead, we used this much, cut it by more than half. That saved cumulative energy equivalent to 25 years of current use. And meanwhile, renewable output doubled, yet with 30 times less cumulative impact than the savings. Renewables, though, get virtually all the headlines. You can see them on the roof or the skyline, but energy is invisible, and the energy you don't use is almost unimaginable. And yet saved energy is avoiding about twice as much carbon each year as renewable growth is, and the potential savings keep growing. Around '75, our government and industry said that the energy needed to make $1 of GDP could never go down. A year later, I heretically suggested it could drop 72% in the next 50 years. So far, it's dropped 58% in 43 years, but just the innovations already added by 2010 can now save another threefold, twice what I originally thought, at 1/3 the real cost. And today that's looking conservative because integrated design, that is optimizing buildings, vehicles, and factories as whole systems, not as piles of parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. Professor Allwood's group at Cambridge University says that global energy use in 2005 was only about 1/9 as efficient as physics allows. That is, the second law efficiency averaged about 11% for the world, or 14% for the US. So including passive options as well, they said that about 85% of energy demand could be practically avoided using current knowledge and available technologies. I think that's a bit conservative, but whatever the right number is, integrated design gets us closer and cheaper. And I'll illustrate that with diverse examples that start in other sectors to set up some concepts that I'll then elaborate for industrial systems. Now, economic geologists know that in minerals reserves, the identified deposits profitably extractable with current technology and price are only a small part of the whole resource base. Most energy analysts also narrowly define reserves of energy efficiency, like the bright green zone in these mineral resource definitions. But the actual energy efficiency reserves are several fold larger than are now typically recognized and captured. And the missing majority is hiding in plain view, exploitable by integrated design. This geological analogy is good on quantity, but it breaks down on cost. Ore bodies are finite assemblages of atoms, and that's depletable. But energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. That's documented in an 11-month-old peer-reviewed paper called How Big is the Energy Efficiency Resource? Just search on that title. Its evidence across all sectors shows that unlike oil or copper, most new energy efficiency reserves cost less than the ones we've been exploiting, because they come not from adding more or fancier widgets, but from using fewer and simpler widgets, or artfully chosen, combined, timed, and sequenced. So how do we do this magic? Well, let me start with a little mental calisthenic. One of my early mentors, the inventor Edward Land, said, "Don't undertake a project unless it is manifestly important and nearly impossible." He also said, "People who seem to have had a new idea have often just stopped having an old idea." That's the hard part. And Asian tradition similarly urges us to seek original mind, beginner's mind, child mind, opening ourselves to new ideas by shedding all assumptions and preconceptions. So in that spirit, here's an example from Caltech's late great aerodynamicist Paul McCready. For decades, textbooks on creative thinking have posed this problem as find the solution that connects these 9 dots with just 4 lines without lifting your pen from the paper. So you're supposed to think 1, 2, 3, 4, oops, 5. 1, 2, that isn't going to work. And you're supposed to figure out to think outside the box, which is where that expression comes from. But one day a student startled her professor by saying she figured out how to do this with 3 lines. Gee, 4 was hard enough. How do you do it with 3? Dots are infinitely small. Well, actually, these are rather plump dots, but it looks like you don't have to go right through the center of them, so if your paper's wide enough, you can do the Z for Zorro trick. And then the students started to feel rather liberated. You know what happens then? They start to solve this problem in 1 line. There are a lot of good 1-line solutions. I'll give you a few to get you started. If you're Japanese, you might think of the origami solution. If you're a geographer, you might use a very long line. If you're a mechanical engineer, we have any of these now? Yeah, tool using critters, so you can get a tool called scissors. There's no rule. If you're a statistician, you might crumple up the paper, and then if you stab it enough times over and over again, the pencil eventually will go through all 9 dots and stay next to it. And the one I like best came from a 9-year-old girl who said, "You didn't say it had to be a thin line." So I used a really thin line. And so as McCready said, this tyranny of the word "the," find the solution with 4 lines, puts us back in the box and keeps us from being more creative and coming up with more elegantly frugal solutions. So with beginner's mind, never having built a house before, so I didn't know what was impossible, 37 years ago I did the conceptual and energy design of this owner-builder house where Judy and I lived 2,200 meters up in the mountains near Aspen, where temperatures used to drop as low as minus 44 Celsius with up to 39 days of continuous midwinter cloud. And yet, we have no heating system. Omitting the heating system subtracted slightly more construction cost than was added by the super insulation, super windows, and ventilation heat recovery that eliminated the heating system. So this house helped inspire the German and then European passive house movement. The central atrium, seen here in a February snowstorm, has so far produced 76 passive solar banana crops. An analogous approach actually works also in Bangkok, and almost everyone in the world lives in a climate somewhere between Bangkok and Old Snowmass. An integrated design gives many benefits from each expenditure, so this white arch has 12 functions, but it has only 1 cost. Now, our integrated design with Clay Nestor's team at JCI. Clay, are you here somewhere? Hi. To retrofit the Empire State Building, saved 38% of its energy with a 3-year payback. And then 3 years later, our cost-effective Denver retrofit saved 70%, making this half-century-old federal complex more efficient than what was then the best new U.S. office. Intensities are in green. And that in turn is less than half as efficient as our own passive net positive no mechanicals office. And now there's a Bavarian building using 3/5 less energy than ours. And yet these technologies all existed over a decade ago. What mainly improved is not so much technology as design, the way we choose and combine technologies. And that's still going on. So that Empire State Building retrofit started by remanufacturing all 6,514 windows on site into super windows that pass light but block heat. And that plus better lights and office equipment and air handlers and so on cut the maximum cooling load by 1/3. So then renovating smaller chillers instead of adding bigger chillers saved $17 million in capital cost, which paid for most of the other improvements. and cut the payback to 3 years, or less than 1 year if we counted non-energy benefits to the owner or tenants. A major energy service company, by the way, also offered a 3-year payback with disintegrated design that yielded savings 6 times smaller. They did not get the job. Similarly, in 6 muggy Indian cities, 1.5 million square meters of offices integratively designed by Rohan Parik's team with help from Peter Rumsey, use up to 80% less energy than the Indian norm. They cost 10 or 20% less to build with superior comfort and satisfaction. And glare-free lighting, as you see it in that big floor plate on the right, is delivered throughout by contract. If workers complain of glare and anybody wants blinds, the architect doesn't get paid. Now, saving energy is a bit like eating an Atlantic lobster. There are these big obvious chunks of meat in the tail and the front claws, but there's a roughly equal quantity of tasty little morsels tucked in crevices that need some skill and patience to dig out. And we need to go for the whole lobster. We went to a lot of trouble to grow all that. Or to pick a different culinary metaphor, the Singaporean master engineer Lian Gok says, like Chinese cooking, use everything, eat the feet. But thinking that energy efficient design is about choosing and installing energy efficient equipment is rather like supposing that if you just toss good ingredients in a pot and heat it up, you'll get a tasty dish. Efficient systems like good cooking result from whole system design, because even the finest ingredients will not make a great meal unless you use a good recipe and a skilled chef to combine the right ingredients in the right sequence and manner and proportions. So you have to do the right things in the right order. And for example, most lighting retrofitters start by installing higher efficacy sources and better controls, but the IES fundamentals rightly tell us first to improve the visual quality of the task, then the geometry and cavity reflectance of the space, then the lighting quality, so you cut hailing reflections and discomfort glare, then you optimize illuminance, then you harvest and distribute natural light, and only then you optimize the luminaires and the controls maintenance and training. And this sequence can often save an order of magnitude more energy with better visual performance and better aesthetics, but most people do it in reverse order, worst buys first. Similar question, how does our innovation center in Basalt, Colorado eliminate its cooling equipment and keep you cool in 11 ways and warm in 10 ways, none of which involves blowing hot or cold air at you? Well, once 30-odd years ago, I asked my hostess in Tokyo why she didn't heat her house. Paper house, winter. And very sensibly, she said, why should I? Is the house cold? Of course, houses have no nervous system, no comfort sensation, only people do. Therefore, we should provide task comfort like we provide task lighting. Look up Katatsu. So our building in Colorado delivers task comfort. Everybody has a hyperchair whose touchscreen or smartphone control delivers comfort of individual requirements. This pretty much eliminates discomfort complaints. It has 3.6 watts of silent computer muffin fans and a couple of electric car seat heaters all run by a lithium battery. And this means we have expanded the range of indoor comfort or indoor dry bulb temperatures to maintain ASHRAE comfort from 64 to 86 plus F. That's under 18 to about 30 C, by exploiting all 6 classical comfort variables, from excellent ceiling fans to super windows that slash the radiant lows. We rigorously reduce unwanted internal and external heat gains and recover 93% of the ventilation enthalpy. Like an Aspen skier dressed in a down jacket and sunglasses, this building is nearly twice as airtight as a passive house. It's super insulated. It's passively cooled by active exterior shading and natural ventilation, including automated night flush to cool the phase change walls. And therefore, we don't need such other passive options as ground coupling, groundwater coupling, geothermal heat pipes, a seasonal storage ice pond. We didn't need active non-refrigerative cooling, which could be evaporative desiccant absorption, adsorption, hybrids. We certainly didn't need refrigerative cooling, whose efficiency we can triple. I'll tell you how later. We didn't need fancy storage and controls. And even in humid climates, a comprehensive approach like this can save around 90 to 100% of space cooling energy with better comfort, lower capital cost, and higher uptime. So what do these building examples teach? Well, start with the end-use effect that you intend. Optimize the building as a whole system, not a bunch of components. So the key to cutting construction costs is typically to use expensive glazings. In particular, pay for the efficiency largely or wholly or more through the mechanical shrinkage it causes. Cut out the most capital cost by starting the savings downstream, as I'll describe later. Optimize the sequence and the timing of design steps, and make sure you reward the design professionals for what they save, not for what they spend. Timing matters too. When retrofitting a big glass office tower, super windows plus efficient lights and equipment can shrink the mechanical loads and mechanical systems by fourfold, more than paying up front for the efficiencies that shrank them. Did an ASHRAE centenary speech showing this for a fourfold efficiency gain in this old Chicago curtain wall tower that could pay back in about -5 months on retrofit. So the retrofit was slightly cheaper than the routine reglazing of the failing curtain wall that you had to do anyway. And deep retrofits of all of our big buildings are going to take decades, so let's right time them to make the savings much bigger and cheaper. And if you go to retrofitdepot.org, you'll find some tools for doing that to a portfolio. Now, similar design logic applies to automobiles. The propulsion system, the powertrain, loses about 4/5 of the fuel energy before it gets to the wheels. But our savings should start at the wheels, and here's why. Just 1/5 of the modern car's fuel energy reaches the wheels and moves the car. And of that tractive load, nearly half heats the air that the car pushes aside. Most of the rest heats the tires and road. So only the last roughly 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But it's worse than that, because 19/20ths of the mass you're accelerating is the heavy steel car, and therefore only 1/20th of that 6%, or about 0.3% of the fuel energy, ultimately moves the driver. Not very gratifying after 1/3 centuries of devoted engineering effort. Moreover, both the acceleration and the rolling resistance depend on mass, which therefore causes most of the tractive load. Now, automakers work hard to cut losses, mainly in the powertrain, because that's where most of the losses are. Much as Willie Sutton said he brought banks because that's where the money is. But reducing powertrain losses is harder than reducing tractive load. It's had a lot of past effort, and it's less rewarding because saving 1 unit of energy in the powertrain saves 1 unit of fuel in the tank. But saving 1 unit of energy at the wheels saves an additional 4 or 5 units you don't need to lose getting into the wheels. So it leverages 5 or 6 units of fuel savings in the tank. So we should first reduce tractive load, especially by taking out weight, then improve the powertrain. The powertrain then shrinks for the same acceleration, F equals ma. That saves more weight, and also it saves capital costs to help pay for the lightweighting. Same story as shrinking mechanicals in buildings. So using that logic, 19 years ago, we designed an ultralight carbon fiber electrified hypercar in the form of this 4 to 6-fold more efficient mid-sized SUV. Toyota, 7 years later, designed a 70% lighter carbon fiber plug-in hybrid sedan. 2013 brought to market this profitable quadruple efficiency carbon fiber electric car I'll describe in a moment. But even 1 ton lighter aluminum fleet vans like this hybrid we developed and road tested a decade ago could save 1/5 of U.S. light vehicle fuel and lower life cycle costs with no subsidy. And then carbon fiber autos can end up saving more oil than Saudi Arabia lifts, but with simpler designs they can be made at normal cost. And we know that because BMW did it 6 years ago with this carbon fiber electric car that I drive. The i3 reportedly made money from the first unit off the assembly line. And Sandy Monroe, the normally understated costing wizard in Detroit, called it the most significant vehicle since the Model T and the most advanced vehicle on the planet. Validating our claims in the 90s, its carbon fiber is paid for by needing fewer batteries, and fewer batteries recharge faster. The integrated design decompounds mass far more than usually assumed. The manufacturing is radically frugal and also confirms the ability to get rid of the body and paint shops, the two hardest and costliest steps in automaking. It's much better for workers, and some overlooked synergies between ultralight materials and electric traction quadruple its efficiency without compromise and with a lot of driver advantages. That's one of 15 existence proofs in a, I hope, forthcoming SAE paper. Now, to make a car half to 2/3 lighter, you have to go repeatedly around the design spiral or design cycle. You start off making the vehicle as light and slippery as you can think of to cut its tractive load at least in half, and then you can afford smaller, more advanced powertrains, smaller, lighter chassis components, less brakes to stop it, less suspension to hold it up. And all that takes less space, so you have more crush space left for safety. And next, you keep going around the spiral because the less weight you have, the less weight you need. As components, as structural loads shrink, the components get smaller. And many big parts actually disappear altogether. Quickly, you get to a good, say, series hybrid that can eliminate, let's see, transmission, clutch, flywheel, axles, differentials, drive shaft, U-joints, starter, alternator, 9 things so far, each of which takes away more mass, and then you go around the spiral some more, lose more mass. And at first it looks like the special materials and powertrain and design may raise your manufacturing cost, but after more mass decompounding, you end up needing so little carbon fiber and such a small powertrain that manufacturing the advanced composite structure gets a lot simpler. Those two savings pay for the carbon fiber, making the ultralighting roughly free, as BMW just demonstrated. Now, designing our uncompromised 4 to 6-fold more efficient carbon fiber electric SUV 19 years ago required us also to organize the designers differently. The basic design didn't use the usual 1,000+ engineers. It used 7, all around the same table, and collectively responsible for dauntingly ambitious whole vehicle requirements. Each engineer was responsible for one major vehicle system or function, but for those, we deliberately wrote no requirements because we didn't want him to make his problem into her problem. We wanted the whole team to have to design a highly integrated vehicle together. So 2 of the engineers were not comfortable without their very own requirements. We replaced them in the first week or 2, and it went fine, and we got the desired results. Toyota asked how we did it. We told them how came their 70% lighter Quad X that you saw earlier. I invite you to think this in mind, keep this in mind if you're thinking of doing industrial design. It's a very powerful process. Now, you also have to design in the future, not in the past. When the Soviet Union in 1960 shot down Francis Gary Powers' U-2 spy plane, Kelly Johnson did not say, I'm going to design a slightly better U-2. He said, I want to own the skies for decades. We'll do a Blackbird. I don't know how, but we'll figure out. Which they did. It took about 13 months. Because Johnson understood that such an airplane was impossible within the conventional design context, because design is like a rubber band. If you try to stretch it too far from the conventional design space, you encounter more and more resistance, and eventually it breaks. But if you jump to the new design space that you really want, you can stretch the rubber band back as far as you have to for technologies that aren't ripe yet, and then as they mature, the rubber band relaxes to where you want to be. Now, these ideas, these examples from buildings and autos now set us up to cultivate beginner's mind and radical efficiency in industry, which uses half the world's energy and electricity. My team's latest 40-odd, probably by now over $50 billion worth of industrial integrated designs have generally found about 30 to 60% retrofit energy savings paying back in a few years. And in new builds, about 40 to 90+% savings with generally lower than normal capital costs. So this is far better than this brown retrofit zone where most energy service companies deliver disintegrated design. It's a bit better than what may be the best of the ESCOs. And our better results come from rethinking industrial processes and redesigning basic elements like pump, fan, and motor systems that are often somewhat neglected. For example, in both buildings and industry, better pipe and duct design can save about 80 or 90% of friction, and if everybody did this, hypothetically, it could save about half the world's coal-fired electricity, typically paying back in less than a year in industrial retrofits and instantly in new builds. Now, the methods are simple. You use big pipes and small pumps, not small pipes and big pumps, and you lay out the pipes first, then the equipment. But such rearrangement of designers' metal furniture remains largely unnoticed and unpracticed because it's not a technology, it's a design method. And few people are yet thinking of design as a scaling vector. Let me dig a little deeper into these two changes in the design process. First, on specifying big pipes and small pumps. Well, friction in a pipe falls as roughly the 5th power of its diameter. So how fat should the pipe be to optimize the friction? Well, all but one of the engineering textbooks we've been able to find say to make the pipe just as fat as will repay its extra cost over the years from the same pumping energy. But that's wrong, because it leaves out the capital cost of the pumping equipment, which must also be big enough to overcome the friction. And therefore, the pump, motor, inverters, electricals size and roughly their capital cost will go down as nearly the 5th power of pipe diameter. And yet the capital cost of the fatter pipe goes up as only about the 2nd power of diameter. So when you optimize the pipe as a component, you're pessimizing the system. When you optimize the whole thing together, you yield fat pipes, teensy little pumps that look like somebody slipped a decimal point, and the total capital cost goes down. Okay, so far? This is not rocket science at all. It's only hard because it's simple. Now the second shift in design is even simpler, even harder. That's laying out the pipes first, then the equipment. I mean, that's the opposite of the normal practice where you put the tanks, boilers, whatever, in some traditional, arbitrary, convenient place, and then you call in the pipe fitters and say, please come connect point A to point B. But by then, A and B are rather far apart. Other stuff got in the middle. They're the wrong height. They face the wrong direction. And by the time the pipe snakes itself across the space, all dressed neatly at right angles like they teach us in trade school, the friction is 3 to 6 times what it would have been with a straight shot. Now, the pipe fitters think this is great. They pay by the hour. They mark up the extra pipes and fittings. They don't pay for your bigger pumping system. They don't pay your bigger electric bill forever. But for you as owner, it's smarter to use fat, short, straight pipes than skinny, long, crooked pipes. In a Dutch industrial pumping loop case, this approach cut pumping energy by 7 to 12-fold with lower capital costs. With the free bonus, it saved also 70 kilowatts of heat loss with a 2-month payback because short, straight pipes were easier to insulate than long, crooked pipes. And then belatedly, I realized we had left out 8 additional benefits we should have counted and captured, each justifying even bigger savings. The system's more compact, it weighs less, it's quieter, those all have a value. It has a wonderfully clean layout for maintenance access, reducing maintenance costs, but it'll need less maintenance because there's less stuff to go wrong. Uptime will improve. There's more flexibility for later debottlenecking if needed. I later estimated that if we had properly counted and valued those extra benefits, we would have saved not 86 to 92% of the pumping energy, but probably nearer 98%, and the capital cost would have been even lower. And by the way, later we added some piping in my own house and saved about 97% of the friction and pumping power. The design changes we need are so simple you can grasp them just from a sketch or a photograph. In practically every building and factory, a critical pump with an in-place spare is laid out like this, so the flow always goes through 2 right-angle bends. Friction. Why not lay it out like this so the main flow has no bends and also fewer valves? And the same logic applies with identical pumps in tandem, a very common arrangement. In the Oakland Museum in California, our colleague Peter Rumsey retrofitted an efficient piping layout, wide joint, fat pipes, sweet bend, diagonal, in the condenser water pumping loop, and that cut the pumping energy by 3/4 with a 2 or 3 month payback on retrofit. It also eliminated 15 pumps that will never again waste energy and maintenance costs. Then he also repiped the chilled water loop in a similar fashion and added variable frequency drives, doubling the flow and saving 85% of the energy. And he simply asked the pipe fitters to lay out the supply pipes as if they were drains. Another part of their brain knows if you put elbows in drains, they'll clog. How do most big buildings pipe cooling tower water back to the condenser? Yeah, it looks like that in Oak City. But if we lay it out instead the way Peter does, everything gets better. And the only obstacle is force of habit. We should bend minds, not pipes. What does such savings mean for the pumps and fans that use half the torque of the motors that use over half the world's electricity? Well, from the fuel burned at the power plant to the end use, there's so many successive losses compounding that only 1/10 of the fuel energy comes out the pipe as flow. But now turn those compounding losses around backwards, and they become compounding savings. And every unit of friction or flow you save in the pipe saves 10 units of fuel cost, emissions, and global weirding at the power plant. Also, as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. So while you're making the pumps and fans and motors about 5 or 10 times smaller, you can also do 34 other things to the motor systems that collectively save roughly 3 to 5 times more energy than just the 2 usual improvements, high efficiency motors and adjustable speed drives. And the cost per say kilowatt hour goes down by about 4 or 5-fold, because if you do the right 7 improvements first, you get 28 more as free byproducts, again, the right steps in the right order. So our 1989 systems analysis of this potential examined induction motors in red, synchronous in yellow, DC in green, and our system boundary was from the electric meter to the input shaft of the driven machine. So we counted the efficiency upstream in the wires and controls, in the motor itself, and in the mechanical torque transmission to the load. But we didn't count the pumps or the pipes or the valves, etc. And altogether, we could cumulatively save in the drive system nearly half the 1986 total drive power energy in the U.S., as shown in blue, with paybacks typically under a year at a nickel rate. And that matches Emery's estimated savings. It's twice IEA's estimate and a lot cheaper. So I think after a third of a century, the synthesis merits a thorough update. Now here's a practical example of improving fluid handling. It's a conventional crude distillation unit at the front end of a refinery. It looks something like this. It costs over $30 million to build, and 36% of that is for piping. So we asked where the pumping energy goes, and we found some fat opportunities to wring out a lot of it, particularly as I've just described. And a standard nominal design would use about 12 times the theoretical minimum pumping energy. So we started redlining the standard design and finding a lot of opportunities to untangle the pipe noodles. You see something they missed? Let's see, look around here. Where's the Y joint? And then the result of that first pass at untangling this pipe spaghetti was a lot simpler, and it was several folds smaller than the original footprint. That's got to be worth something. And a practical design would use about twice that much pumping power as the theoretical minimum, but about 6 times less than the normal design. Then satisfying insurance and health, safety, environment requirements, HSE, spreads things out again. So although you can still see some further opportunities to eliminate some elbows and cut friction and shrink pumps, but in this case it was enough to triple the pumping energy for required physical separations between pieces of equipment. Often there are some other smart ways to achieve HSE goals, but let's conservatively leave them out of this conversation. And then repackaging the result, although it didn't completely fix some layout issues you could readily spot, still turned out to be a lot simpler and smaller than the original standard design. And after adding a little more pumping energy for certain operational considerations, bottom line, the redesign still shrank the same pumping energy by about $250,000 a year. But most interestingly, the capital cost of the piping went down by 2/3. So the entire cost of building this distillation unit went down by 24%, or over $7 million right up front, without even valuing the safe space. With more effort, I think we could do better, but this was a promising start. Now, if a 10x pumping savings sounds to you incredible, just reflect that at this instant, your heart is pumping blood about 10 times as efficiently as it would if you used standard industrial pumping piping design to move water and other liquids. That is, if your 100,000 or so kilometers of fractal blood vessels had the design and friction of standard industrial piping, you would need a heart bigger than your body, which would be really inconvenient. But in fact, your third of a kilogram, 1.5 watt heart suffices, because your blood follows nature's standard design, which is called laminar vortex flow. In San Rafael, PAC Scientific's founder, Jay Harmon, has developed this new kind of hydrodynamics, displacing centuries of supposedly mature practice. He's an ocean captain and a keen observer of nature and why things are the shape they are, like Darcy Thompson. So he looked at this ropey Fibonacci spiral in a vortex running out of the bathtub, froze it in acrylic, realized it had to be the minimum energy shape for the air-water surface, and then brilliantly inferred that perhaps a rotor with that shape could move fluids with minimum energy. So that's what he did in these fan and pump designs. And the rotor at the lower right, therefore, emulates the water vortex at the upper left. And now there's a growing family of products like that that can often improve pump and fan efficiency 20 or 30%. And they have a lot of other applications we've barely begun to imagine. One simple one that's been quite successful is in the big tanks that hold purified municipal water before it's sent out for use. And that water has to be continuously recirculated to keep its disinfectant active. And normally that needs a giant rotor like this one, driven by hundreds of kilowatts. But the fist-size version here, driven by 25 to 50 watts, outperforms it by setting up ring vortices that require almost no energy to keep going. And those biomimetic rotors' performance does not depend on scale or on Reynolds number. So there's even more than we thought to be saved in the 25 or 30% of global electricity that runs pumps and fans. These are, marvels of Victorian technology, but learning from nature's 3.8 billion years of design experience can teach us even better how things are made, how they work, and how they fit. Layout, as in the refinery example, also proved critical when Paul Westbrook and I co-led a charrette 15 years ago that made Texas Instruments semiconductor wafer fab 40% less energy intensive and 30% or $230 million cheaper to build, which is why it was built in Richardson, Texas, not in China. Its system efficiency is actually eliminated in one of the 2 utility floors. And Paul's new book, The Joy of Efficiency, updates the data on the proof of RFAB's performance, and also TI's 12-year spread of its methods to cut company-wide chip-making energy intensity so far by 62% per pattern. There's a long way to go. Water cut by 56%, greenhouse gases 57%. By the way, our team's next chip fab design for another client showed how to save roughly 2/3 of its energy use and half its capital cost while eliminating all 22,000 tons of chillers and replacing them with any of 3 natural cooling methods that can yield over 100 units of cooling per unit of electricity. Speaking of cooling, if you do want water-cooled centrifugals, Liang Bach and Peter Rumsey routinely triple the efficiency of those systems from this standard to here by using these straightforward methods, with total capital cost going down and comfort and uptime going up. And the whole system, supply fans through cooling towers, adds up to 0.52 kilowatt per ton if you go to a dual chilled water temperature, separate coils for condensing and sensible cooling, and that raises the savings to 70% from normal practice, but again, it works better and costs less. There is one trick to it, and that's rethinking the cooling coils, because Mr. Lee's design for Rex Willis Carrier's 1921 misinterpretation of his lab data, which he thought were telling him that condensation in a coil is film-wise and airflow is turbulent, but then the late Sam Luxton in Adelaide built a wind tunnel and measured it and found just the opposite, it's laminar and dropwise. So if you turn the usual deep, dense coils around sideways and blow the same fast flow of air through the same mass of copper at a quarter of the face velocity, keep the face velocity under a meter per second, under 200 mpm, then you preserve those droplets and their extra surface area, so you get 29% more dehumidification per unit of sensible cooling. The airside pressure drop goes down by a factor 20. The fan gets smaller, the evaporator load shrinks, the whole cooling system shrinks. It's not that hard to do, but it means beginner's mind. And there's similar logic you can apply in big data centers. For example, 2/3 of the fuel fed into the power plant is lost in the plant and the grid, and then half the metered electricity is lost before it gets to the servers, running mainly the cooling and uninterruptible power supplies, which together are half the capital cost. And then half the energy that reaches the servers doesn't get to the chips because it's lost in inefficient, usually very part-loaded power supplies, and a lot of fans to take heat that largely shouldn't be there off the motherboard into the room so we can do dumb things with it. And then the next problem is severe underutilization of computing resources because of insufficient virtualization and the like. These are, by the way, about 10 or 15-year-old numbers. I'm sure some things have got better since then. And then the next, the resulting energy flow down here is about to disappear, so let's magnify it. The next problem is bloatware, running a lot of unnecessary threads and processes and making simple computing tasks complicated because CPU cycles were cheaper than programmers' attention and somebody else bought the energy. And then downstream of that, you might even have inefficient business processes. So altogether, there's a few hundred thousandths of the original fuel energy at the power plant that ends up creating customer value. So where should we start fixing this? Think of the pumping example. Think of the car example. Start at the end. Start downstream. First, write elegantly terse code optimally compiled with the goal that every compute cycle is a needed and wanted one. And I had assumed this could save an order of magnitude in the compute cycles, but recent tests suggest it's 2 orders of magnitude. And now that we do so much on mobile devices, that means battery life, so it's become valuable again. I understand there's some good news coming about some of the server operating systems. And then we can make the servers themselves at least 4 times more efficient, probably a lot more today. And they will need a lot less cooling and power supply. There are smarter ways to do those. We can even save half the utility losses by using fuel cell trigeneration, cheaper than the uninterruptible power supply it displaces. So multiply those savings from downstream to upstream, and you get at least 2, maybe 3 orders of magnitude energy savings. In the actual installation, by the way, for which we made this diagram to educate our client, they still rejected most of our recommendations, so we were only able to triple efficiency at the same capital cost. However, our partner EDS said that had our recommendations they agreed with, all been adopted, we would have saved about 95% of the energy and half the capital cost, and that's without software improvements. Integrated design can also transform energy supply technologies. So RMI's Shine team wrung out half of photovoltaics balance of system cost, which at the time was 60 to 90% of total cost, enabling DOE Sunshine program. And then we led 2 more rounds with industry of whole system redesign. And the 3rd round recently yielded a 2x8 module solar packet or solar Lego block, roll on, roll off from a truck, snaps into place and you're done. So it's a highly integrated industrial product with 98% fewer parts, 10% less land use. It's all optimized for assembly, shipping, materials, civil works, electrical and mechanical installation, and wind loads. And this could unlock massive benefits across the value chain, because it can match or beat wholesale power prices without needing transmission lines. It's a community scale, say a 10th to several megawatts ground mount PV system that can feed unsubsidized 2.5 cent power straight into the distribution system. That's below Sunshine's 3-cent goal for 2030. And today you can buy equipment like this in Australia, and Texas co-ops are ordering it. Heat pumps are also advancing nicely. Some of them produce 160 to upwards of 200 Celsius, but it's at least as interesting to find the many processes that need low temperatures and low lifts, and yet are now using fossil fuel boilers and furnaces. So commercialized now in Switzerland, coming in the US is a miniature 200,000 RPM domestic hot water heat pump that beats 60% of Carnot efficiency by optimizing the small lift that's actually required. The best heat pump story I've heard lately is from J.B. Straubel, then at Tesla, and his first design decision about their all-electric, all-PV battery gigafactory in Nevada was that it would have no gas pipe. And his colleague said, "JB, you got to be nuts. We're going to need process heat. Everybody knows you do that with gas." He said, "Just watch." So he went off for the air permit, came back with it after a half hour over-the-counter transaction. Normally it takes 6 months if it's uncontested, if you're burning stuff, but not doing combustion. It's real easy. What is 6 to 12 months worth in the battery business? And then going all electric drove serious innovation. Their biggest load was redistilling a key solvent, and normally that's done with a megawatt thermal of gas boilers. He ended up doing it with a 15 kilowatt electric heat pump that would fit twice under this table. The 98.5% energy savings is obvious because it's only a 1.5 Kelvin lift. So why are we burning gas at over 1,000 degrees to do that? And there are surprisingly many process heat modes that are like that. But again, the most powerful interventions come not from finding a better widget, but from starting with beginner's mind and asking a different design question. For example, there was a new environmental manager at Safeway who was asked to figure out what to do with the nasty fatty waste left from cleaning out pipes in their ice cream factory. It's called Clean in Place. And his answer was, "Gee, why are we running in batches instead of continuously? We can just keep track of the mix zone where you're transitioning from one flavor to the next flavor and package that separately and sell it as, magical mystery tour, mixed flavor. We don't know what it is either, but you'll really like it." And then think about what that does for the economics. You earn your average margin, but you save the raw material cost that was being lost in clean out and the waste disposal cost and the time and materials of cleaning the pipes a lot more often than hygiene requires. You get extra production at no capex, and actually they were able to sell the thing at a premium, and it probably didn't cannibalize their products, but their competitors more, because nobody else had anything like this. Isn't that juicy or tasty? So, a second case, I was able to find some substantial conventional improvements in a nearly new high Arctic industrial diamond mine. And one day I got curious about their grade tonnage distribution, asked to see the curve. There was an anomaly in it. And then I asked, well, how do you assay diamonds in your kimberlite mine? And this turned out to reveal a promising way to get rid of the mine. Normally, you drill, blast, dig, load, haul, crush, separate, and if there were any kind of goose egg diamonds there, they'll probably be broken before you even know they're there. But it turned out you could get rid of the mine and the mill and most of the cost and get much better recovery. The way you would do that is to ask different questions. The way they assay the diamonds is caustic fusion. You dissolve the kimberlite in hot caustic soda. So why don't we build a sandworm like the Frank Herbert Dune novels that will burrow down into this carrot-shaped bunch of kimberlite and dissolve it with hot caustic in its gut and poop out diamonds, come along behind it and neutralize. And that sandworm's going to have to be made of really fancy alloys. Hot caustic is bad stuff. On the other hand, you could make it out of practically pure unobtainium at orders of magnitude higher materials cost and still make a lot more money that way. And the boss said, that's such a good idea. I'm prepared to abandon everything you see here a third of the way through the mining plan and switch over to your method. Unfortunately, he was hired away soon thereafter, so it never happened. But it's still probably a good idea. And then there was a third case where my team found that 108 kinds of retrofits in the world's largest platinum mine, 43% of them needed no capital, could save over 2 terawatt hours a year, over 5 megaliters of diesel a year, over 2 megatons a year of CO2. That's all pretty straightforward stuff. But the highest leverage interventions were not about the mining equipment or the process, but about the miners. And it turned out to be quite an eye-opener. If you took these lead-acid battery incandescent Victorian headlamps and replaced them with modern, LED lithium, no cable, instead of a thumb-thick cable, you'd see better and strain your neck less and be able to move around better. It's kind of like a sauna a kilometer under South Africa, so we introduced phase change vests that cool the skin, not the air, minimize latent loads underground. Instead of strings of incandescent lights, so you'd either look at the light or look at the black rock, and either way you couldn't see. We suggested painting the walls white with efficient indirect lighting. The workers were getting hydrated only at break, not continuously. They never heard of Camelback stuff. They weren't getting any electrolytes, but rather diuretics. They were drinking sweet tea. So just fixing the physiology made things a lot better. And then we separated the provision of coolth and dryness, ventilation, filtration, and coolth. They were blowing tens of thousands of tons worth of coal electricity, chiller cold air down a kilometer sideways to try to cool the working where the workers were. That doesn't work very well. But instead, we could exhaust heat with heat pipe risers that wouldn't take much of the precious shaft area and would be a lot more effective. And very high leverage would also come from giving information to the miner at the face with a miniature assay device, and also paying them to hoist up tons of value, not tons of waste rock or old timbers or dead donkeys or whatever was tons, because they were paying by the ton of whatever. So again, asking different questions gives different answers, and it's not all about the equipment. And then there was a different mine up in West Africa, a mountain iron mine. And living near a ski town, I noticed these Austrian ski lifts and wondered if they could be equipped with buckets rather than seats and run backwards to lower the heavy iron ore down to the port. And yeah, the same vendors offered that option. You get 93% of the gravitational energy back, 5 megawatts of it. And then you could make still more electricity by running a purged water table that was a nuisance at the mine down to the dry port through a hydro turbine and sell the water. And together, those two generators without PV would be enough to run a very efficient all-electric mine. No fossil fuels, no emissions, no grid connection. and it turned out to be attractive to resupply by a combination of the ski lift and dirigible, more beginner's mind. So in summary, we're all used to looking for big industrial savings in these familiar 8 places. And that's a good menu, but I would encourage you also to apply 8 simple methods, which I've given examples, 8 different priorities, each with important benefits. And the results are really quite surprising when you put them all together. I also would encourage you to apply some good advice that General Eisenhower gave to make tough problems soluble by expanding their boundaries to encompass more options and more synergies so they include what the solution requires. And let's apply this thinking to industrial process heat, which is, of course, a big deal for making materials like cement, steel. So processes and products are being redesigned to use less heat and cooler and cleaner. But we should start at the end with demand not for energy to make the material, but for the material itself. 20 years ago, our business book, Natural Capitalism, found that U.S. materials flow around 1990 was 99.9% waste. So here's how we're starting to think about this opportunity. I'll end with a few slides on this and use mainly steel and cement examples. So first, change how we deliver the services that now need energy-intensive materials. The remote infrastructure that provides 6 kinds of services to buildings and the pipes and wires in between can often be replaced by on-site methods at lower cost to society and probably to the developer, saving a lot of steel and concrete and plastic pipe. Also, replacing separate specialized buildings with multi-purpose buildings and multi-use zoning can save building space and travel and roads and bridges. 3D printing enables boat-like structures using no factory, little metal, less transport. A chemical plant may use 80 or 90% of its capacity and energy to separate unwanted byproducts, but etching microreactors into a stack of silicon wafers can often control the reaction so precisely that only pure product is made. And both these innovations allow local manufacturing, displacing steel vehicles riding on concrete and steel roads between steel and concrete warehouses. Shared and connected mobility likewise saves roads and parking. So does virtual mobility that just moves the electrons and leaves the heavy nuclei at home. Designing cities around people, not cars, saves 1/3 of the concrete and 2/3 of the driving, while greatly improving quality of life. And then, just like mobility as a service, which now has 50 million drivers serving 1 billion ride-hailers, natural capitalism's solutions economy business model can lease structural performance rather than selling tons of cement. So the provider and the customer both make more money by using fewer tons. And the provider can also reward the structural engineers for delivering the best performance with the least material. When I suggested this a couple of years ago to the chairman of a giant cement company, he said, yeah, good idea. I have 200 people working on that business model. So I got to go back and see how they're doing. Rewarding elegantly frugal design can often bring an order of magnitude more work from materials. For example, substituting tension for compression structures typically gives better strength, aesthetics, and cost with 1/8 the normal tons. Fabric forms optimal shapes can save upwards of half the concrete in beams and sheets and other common shapes to deliver the same or better strength and stiffness. And then the weight savings snowball because you need less strength to hold up less weight. The overall saving in making all kinds of buildings from concrete and steel is at least 2-fold from better structural design. Nature is also rich in incredibly mass-efficient designs we can imitate, from trees to bird bones. MIT's self-assembling, hooked-together miniature lattice structures, molded from conventional thermoplastics, are as strong and stiff as solid elastomers, but as light as aerogel. Then make them out of carbon fiber, you gain another order of magnitude, carbon nanotubes another order of magnitude, and we can make nanotubes from sugar, water, and sunlight by the bacterial enzymes that hummingbirds use to weave their nests. And by the way, this is not just theoretical. These lattice structures just produced an airplane weighing 59 times less dense than normal with better aerodynamic performance. It eliminates movable flight surfaces, but the entire shape, like a bird wing, passively adapts continuously to real-time flight conditions for aerodynamic optimization. Revolutionary stuff just coming out of the lab. 3D printing of materials-frugal bridges, look at this light, airy structure, is becoming popular in China, Holland, Dubai, elsewhere. Here's a swooping 3D printed steel bridge about to span a famous Amsterdam canal. Here, the whole structural faculty of TU Berlin is testing a 13-meter free span supported by 3 carbon fiber ribbons 1 millimeter thick. We can also substitute low or negative carbon materials like wood and bamboo for steel and concrete. The cheap husk of the rainforest restoring Indonesian sugar palm has lignin fibers with 7 times less density than stainless steel but comparable tensile strength. And modern materials are also powerful. As you saw in the car example, a thin sheet of carbon fiber composite can save 2/3 of the wood in a glue lamp beam, 30 to 50% of the concrete in a structural panel. Actually, carbon fiber anti-corrosion wraps save the 30 to 40% of concrete you need, not for static strength, but just to cover up the rebar so it doesn't rust. How about eliminating the rust with carbon fiber rebar, carbon concrete composites? And the auto-resistant shell of the abalone is tougher than our best missile nose cone ceramics, but instead of being made with an incandescent furnace, it self-assembles in seawater at 4 Celsius. Conch shell is 10 times tougher still. It's 1,000 times tougher than the basically chalk biomaterials that it's made of. And besides bamboo rebar, whose growth fixes the offsetting carbon, lower negative carbon substituents to dilute Portland cement range from otherwise wasted silica-rich rice hulls and silica fume to fly ash, and some can markedly improve performance. New York's Freedom Power saved 40% of its cement through stronger concrete and mastic compounding, and now the materials are twice that good. They're 10 times as strong as house concrete. In the world's second tallest building, Shanghai Tower, putting a twist in the design shrank the wind loads and structural systems and cut materials cost $58 million. China makes over half the world's cement. They used to make it in shaft kilns, which produced such irregular quality you had to triple the richness of the mix to make sure stuff wouldn't fall down. And that means you triple the fuel savings from switching to modern technology. So if you make cement and rebar to European quality and make buildings last longer, you can cut Chinese cement demand 6 to 10%, steel demand 6 to 8, global rebar demand 13. And better materials also have a lot of indirect benefits from not having to haul so much stuff around. Sea urchin spines use a self-assembling mesocrystalline structure that can give calcium silicate hydrate 40 to 100 times the flexural strength of normal concrete. Imagine what you can do with flexible concrete or analogous new cementitious chemistries, or with biomimetic spider silk, you could weave into cocoon-like rooms. And finally, the world's largest non-agricultural waste stream is construction and demolition waste, which in Europe is a half ton per person per year, but it's especially suited to recycling. There's a Dutch technique for smart crushing with 1/10 the normal force that can selectively liberate the up to 2/5 unhydrated cement for valuable reuse in new concrete. Globally, this can save, they save 2.5 gigatons of CO2 a year. And then molastonite cements like Solidia that stick to themselves let concrete roads be patched up like asphalt instead of having to be torn up and replaced. So these and many other diverse demand-side options for using less cement, steel, and so on multiply to very large savings even before you get to circular economy or all the improvements in processes and heat sources and efficiency. So there's a lot less high-temperature process heat to decarbonize. So basically, we're looking at how you add the missing 8 line items here to the conventional menu. I therefore don't think that heavy transport or process heat are uniquely hard to decarbonize. Of course, none of this stuff is easy, but some sectors like cement, have unique institutional barriers. And yet the hard sector's small number of major players and large combustion devices, their operators' relentlessly competitive focus on the business case might even offer some potential advantages in decarbonization over the messier, fragmented market, multi-million target sectors like light-duty vehicles and buildings. Maybe the main thing that's making heavy transport and process heat look hard is the belief that they're hard. So I hope this little gallery of examples suggests that might not be right. And we're excited to be testing that hypothesis as the next enlargement of the design space for industrial energy efficiency. If anything I've said has surprised you, just remember that remark by Marshall McLuhan that only puny secrets need protection. Big discoveries are protected by public incredulity. I want to thank you all for your wonderful work and your kind and prolonged attention.